All right. Well, it's the top of the hour, so thank you, Igor, for the first hour with your presentation. Well, let's go over to Luke. Luke, you've got sharing privileges, and whatever you'd like to share with us this morning, we'd greatly appreciate it. So I'll turn the control over to you, sir. Take it away.
Hey, very good. Uh, I have a presentation. It's on meteor scatter. Actually, what I do is meteor detection. The project was done as an astronomy uh, project rather than an amateur radio project. So I wasn't trying to make contacts on the tails of the meteors, but that is a function that can be done. One of our club members in Sudbury, Steve, VE3RX, I don't know if he still does that. I know he does moon bounce, but he used to do, at the very least, meteor scatter. And from what he described at the time, this was a long time ago, when I had first started in amateur radio, he was doing the meteor scatter, and he was using CW because most of the tails don't last all that long. So you end up with, you don't have enough time to make an FM contact, a voice contact. Even single sideband is pretty sketchy. So they tend to make very quick contacts because you don't have a lot of time. It's very rare that you'll get a tail that'll last a minute or two, where you would have time. In fact, I've heard FM stations come in off of a tail where you can actually hear some of the music. So it does happen, but it's not that often. So what I'm going to do is I'm going to turn on my presentation, and right here, and go to, move this out of my slideshow. Start from the first slide. There we go. Can everyone see that?
Yeah,
Yep.
it's perfect.
Okay, good. So, well, I'd like to get rid of that. Anyway, I've got a control at the top of my screen here that's kind of getting in the way. Anyway, this is a stock image I picked up off the internet. That is you might as well call that a fireball. You don't see that very often. And that's the kind of thing where that trail that's left behind there is a pile of dust. And that's where the radio signals bounce off of. And the receiver can then get the signal. If you're doing amateur radio, you can do a two-way signal off of something that large very easily, probably multiple contacts, because that trail will last there for a while. The biggest effect is how heavy the winds are up at that level. So I'll get into that in a bit. So basically, there are two types of systems. There's a forward scatter, which requires listening to a distant station that's too far away to hear directly. In other words, the curvature of the earth gets in the way. For example, I'm here in Sudbury. If I were to listen to a North Bay station, that's not a good example. If I'm sitting on the ground, I can't hear a North Bay station, but I had my antenna up at 46 feet, and I could listen to North Bay all day if I wanted to. I could listen to Elliott Lake, Little Current. So I had to pick some pretty far stations. So the idea, I'll show an image of what that looks like. And then the other type of system is backscatter, where people use a radar type setup. They have a transmitter and a receiver at the same location, and they're bouncing a signal off that tail. So they're most often using the same antenna. That's a pretty rare thing, but it's one way of doing it. You tend to hear that kind of thing being done by universities. They do a lot of really interesting things there. So here's an an image of a transmitting antenna, a receiving antenna, and you get the Perseid meteor shower. So you get the radiant. I'm trying to point here. There we go. I'll use my pointer. That looks a little smarter than pointing at the screen. Anyway, there's the radiant. That's where the meteors seem to be coming from. That's the direction that the Earth is traveling into the dust. So you'll get some coming this way, some going that way. But basically, the transmitter bounces its signal off of that tail and it comes to the receiver. Normally, these are too far apart to be heard. So there's a visual image. If you were using light, you get an echo from the meteor trail. So there's an exaggeration, a receiver and a transmitter. Curvature of the Earth obviously isn't that pronounced between the two stations, but far enough that they can't hear each other. And so you get the occasional reception because of the meteor trail bouncing the signal. Now,
What
they're
kind
not
of
the only
distances,
things.
Luke?
Pardon me?
What kind of distance are we talking about with that? Because
That would depend on your setup.
Yeah.
I was reading some setups from some universities and other people who set up their antennas just a few feet off the ground. Some would just set the antenna vertically so that the reflector, it's a Yagi antenna, the reflector is parallel to the ground and the antenna is pointed skyward directly. So it depends what you want to do on the kind of distance that you would get. For example, one of the experiments that I did, it was working in my shop. I have a stereo in the shop with a FM receiver, and it has rabbit ears on it. So I tuned into North Bay station. I can't hear North Bay from the ground here.
Mhm.
So once in a while, all of a sudden, I got something coming in full quieting from North Bay, and then it would fade away and disappear. Most of the time, all I hear is noise. So that's the kind of thing you would get. Now, I have to also point out that meteor scatter is not the only thing that's in the sky that you might get a reflection off of. And you have to be able to see the difference. And I'll show you pictures of what I get on the radio receiver. I use SDRs for receiving. And you can get, I live in Garson, which is on the way to the airport, so you could easily get radio signals bouncing off of planes. You can get radio signals bouncing off of the ISS, although I've looked at ISS tracks time and time again. I have never received one because my antenna was sitting horizontal at 46 feet. So most of the stations that I received, I thought were at the far end, the far west end of Ontario, into Manitoba, and I'd say as far as Saskatchewan. Never did get anything that I could claim went as far as BC. That was too far. I hope that answers the question.
Can I
Yes.
ask you a question?
Yes, thank you.
Luke,
Yeah,
can I ask you a
question?
question?
Sure.
When you have a meteor going through the sky, like, what part of the meteor stream is the best part to hit for your radio signal? Like, is it the tail end of the meteor or closer to the head end of the meteor? Which is the best for
Okay.
reflecting the signal?
The tail.
The tail end, eh?
Any part of the tail is good. The head, I have an image of what a head signal looks like. All you're going to hear is a ping coming off the head. because the head goes from 15 kilometers a second down to a few hundred kilometers a second, a few hundred kilometers an hour in a matter of less than a second. So the head is a 1 in 1,000 hit. It's the tail you're going to get most of the time.
Okay, thanks, Luke.
Okay, so another effect you're going to see here is wind shear. And there's an image there of what wind shear would look like. And that's because there's wind blowing up there at different speeds at different part of the tail. So you're going to see the effect of that in the reception. So that's going to cause a distortion. The signals can add or subtract depending on the timing. So that means when you're receiving, you might get a stronger or a lower signal at different times as you're receiving through a different part of that trail. And the fluctuations are quite significant. You'll see them in the images. So one of the designations that they give these tails is underdense, which means there's not much material there. So the signal reception lasts less than a second. So that's not very useful, but it is detectable. And then there's overdense. That means that there's enough material there in the tail. The radio signal could last from seconds to minutes. And like I said at the beginning, it's usually less than 2 minutes. So there's an example. I'm going to zoom in here. An echo from the plasma ball at the head end of the meteor, it's 1 in 1,000. I'm going to zoom in here. Oops, wrong. How do I do that? Did it before. Okay. I'll have to do it at the end. Anyway, I had that working the other day. I can't remember how I zoomed in. Anyway,
did you use your mouse wheel and a control button? You press the control button on the keyboard and use your mouse wheel?
I'm trying that now. It's not working. So
oh, okay.
I'll have a look at it. But you can see we're at the end of my cursor here. You see that little line on the screen?
Yeah.
And that little hook here?
Yeah.
That's the head end of the meteor slowing down. This is tracking in time.
Wow.
So that speed change, because this is, I think that's 88.1 megahertz. Anyway, that's the reception area there. And this is where the head breaks up and leaves a trail. What you can see, the offset in frequency tells you that's your, the words escape me again, Doppler effect. Look how big of a difference in frequency from here to here. And from that Doppler shift, you can tell how fast that's moving. And not only can you tell how fast it's moving, look how quickly it's slowed down. The Doppler shift is huge here. So that tells you how quickly that thing was moving. So there's formulas that you can use. You plug in the Doppler shift and it'll tell you just how quickly that thing was moving. And it went from this speed to this speed in a fraction of a second. So head echoes, like I said, they're 1 in 1,000. And then if you look at, if I could zoom in, I could show you, but I'll show you on a different one at the end. I've got some separate slides after the presentation that we can look at least one anyway. And you look at the offset from 88.1 to where this thing is, and you can see that the difference here tells you your that's the wind speed that's shifting the meteor trail. And if it's on one side of the actual frequency, the wind shear is going towards you, or if it's on the opposite side, then the wind shear is going away from you, and the meteor, the signal is shifted one side or the other, depending which way the wind shear is, away or towards you. And you can see a little bit of a difference here on the frequency. So it hit a wind shear. Okay, next one. Meteors can enter the atmosphere at speeds of up to 72 kilometers a second, not an hour, a second. We can use the Doppler shift of the transmitted signal to calculate that from the head echo line of sight from the transmitter to the receiver. Like I did on that last slide. If I had, now it's interesting and especially important to know how well calibrated your frequency is on your receiver. Most people who do this kind of thing, to get exact figures, they'll have at least oven-controlled oscillators in their radios, or have a reference that's GPS trained, so that they have extremely accurate frequency reference. Now, I also showed where the wind shear is once the tail settles down. For amateur and economical systems, forward scatter is the best way to go. It's the cheapest thing to do. You use a distant station, should be strong, steady, running 24 hours a day. Now, I used FM radio broadcast simply because it was a cheap setup. TV station, the best is the best, because a TV video carrier is AM analog. And on an AM carrier, it's a steady carrier. It never fluctuates. It doesn't go up and down. Of course, that's why they were trying to get away from it, because most of the energy is in the carrier and it doesn't carry any information. So that's why they wanted to go digital. But those analog TV stations are few and far between now. The other thing you can use are amateur radio beacons. If you wish to try it that way, that would work too. Now, a simple setup, you could just use an FM radio, like I described I have in my shop with rabbit ears. Look up a strong station somewhere between 100 and 200 kilometers away. Just tune in and listen. You're going to hear a hiss most of the time because it's FM and it's noise. And once in a while, you're going to hear a ping, which is really good because that means you got reception off of a head. Or if you get a reception off the tail, you'll hear the station come in once in a while, and you can actually hear music or voices or whatever.
It'll be kind of fluttery, right?
Yes, it would be. Yeah. But I'll show some images that sometimes they could be good and strong and questionable whether it was a typical, I know for a fact, one of them wasn't. It might have been an inversion that came through because it lasted way too long. So the simple setup, the meteor trails will cause the noise level to reduce. A wide meteor trail will cause audio to come in for a few seconds. Head echoes will cause a ping. And like I said, 1 in 1,000, but it does happen, and I have heard quite a few. Because I was listening for a lot. one of the things that I used a SDR Play first. I was using computer with an i7 processor with 8 cores. And because the SDR Play, if you want to set up several receivers, it takes a lot of horsepower. So that i7 processor handled it really well. I could listen to a whole bunch of things all at once. The downside is it wasn't automated. The only thing I could do is I found a program that'll take screen captures every so often.
Hi, what's up?
So anyway, that's what I did. So things that can cause you false echoes: planes, ISS, large objects entering the atmosphere like space junk, atmospheric conditions, sporadic key layer, inversion layers. Now, if you're doing amateur radio stuff, well, some of those are probably beneficial. So they wouldn't be false readings if that's what you're looking for.
Maybe we could bounce something off of that Chinese rocket second stage. It's going to whack into the dark side of the moon.
Yeah, that's a
You
little
heard
far.
about that? You heard about that, right?
Yes, I have.
Yeah.
Okay, so so a more elaborate setup, and that's what I had done. I had a high gain antenna. It was only 4 elements, but it's better than rabbit ears. I built a filter, but that's optional. I bought a preamp, and I did use RTL SDR receiver, USB receiver, my computer, and the software. That was more elaborate. And here's a picture of what I had done. There, it's not very clear, but there's my antenna. Cost me all of $40 delivered from the source. I don't know if they still carry that. I bought this in 2018. It's very light duty. It didn't last the whole winter, probably because the Raven tried to land on one of the elements. One of the elements broke off, or half of the element did. Now, the other thing that I did is I looked at all the stations that we had here in Sudbury, and I was trying to pick a place to listen where the stations wouldn't bother what I was trying to do. So what I did is I built this filter here. I put that first in line after the antenna. I ran the cable in the house. I put this in line with my cable. So it's a helical coil filter.
How big is it?
Pardon me? Is there a question there?
Physical size of that filter.
I couldn't.
Oh,
Yeah, the physical
it-
size of that filter. How big is it physically?
It's about 4 inches wide and about a 1.5 to almost 2 feet long.
Thank you.
And you need a 100-watt soldering iron to do that. When I put it together, what I did is I just laid solder along the joint like this. I cut the solder, I laid the physical piece of solder on there. Then I started running my 100-watt soldering iron from one end to the other, and it made a perfect job.